Welcome to lesson 21 in our series of building the Streamlit prediction dashboard for stocks using the models. Last session we continue working on train predict file and completed the method for linear regression, and now it's the time for the method designed for the prediction system named Arima. What is it? This method will train a pure time series forecasting model that will use only past prices, will ignore technical indicators, volume, or external failures. So this is purely, again, based only on pricing. And it is learning temporal autocorrelation structure. It is more ML machine learning model which can answer to a question like, if price history alone continues behaving statistically the same, what comes next? Let's start working on the code. We have already a definition for the method, and let's add here just what this does. Training well, and we will start with trying to include this into the router. Train data will be prices, tail, and the values. The price side, it's 252. Why it is 252? Because this 252 is a number of trading days in a year. So let's just add here explanation note. 252 is a number of days in a calendar year. Also, I think we forgot here to add prices. Prices, which will be PD series, and we will not need this number data arrays. So with this, we are going now to fit Arima model. Model equals Arima train data orders 510. Just bear with me for a second. We will get back to the line and the explanation. Fitted model equals to model fit model path is OS path join self models directory Arima f symbol Arima joblib, and as in previous joblib dump feed model path, and here return feeded model except e error training Arima symbol for symbol, Arima model for symbol, and string with returning the exact exception. We are, let's go now line by line over the code. We are wrapping all this into the try method, try except, because we don't want our pipeline to fail. We are then declaring a trailing window with number of trading days in year. Thus we are getting enough data to estimate parameters and not too much stale history. We do not want to use all the history because old data can degrade forecasts, and 1 year data is much accurate for predictions than 5 years data, because it has more potential spins that can completely change the approach of model. Also, Arima assumes stationarity after differencing. It's using the recent using the recent data improves the relevance. With this model, we are coming to some sort of hidden assumption, like the next day will behave like the past year statistically, which is strong but explicit explanation. Next, we are going to the heart of Arima, model instantiation. We're creating an instance of the model of Arima. Arima comes with 3 parameters, P, D, Q. P stands for autoregressive lags. This is our, let's add a comment here. Come as values for P, D, Q, E, R. So P comes for autoregressive lags. Our value here is 5. D comes as for differencing order. Our value is 1. And Q is moving average terms. We declare that we are not relying on moving averages. What does D1 do? It transforms like the current value versus the one before it. The purpose of it is removing the trend, makes the series stationary. Autoregression in terms of 5, our p-value, this model assumes interpretation of this is like today's move depends on the last 5 days of moves. We are capturing here short-term momentum or mean reversion. And Q equals 0, no moving average, we are assuming that residual noise is unstructured. So anything affecting the trend is non-structured affection, so we should not consider. No error correction from past shocks. This simplifies stability and convergence, but the side effect of this is that it might or may reduce accuracy. So we are coming with these parameters for the instance of the model that we created here, and then we are feeding the model with this line. What happens here? Stats models that it estimates parameters through maximum likelihood. It solves a nonlinear optimization problem. I don't want to go too deep into mathematical or too much technical thing, but this is just a parameter that we are providing for this method to calculate based on predictions. Why Arima feeding can fail with too little data? Well, we are trying to solve it with 1 year of consecutive data, which should avoid or null this problem, if you will. Strong autocorrelation. We provided 0 as autocorrelation, so it should not affect either. Next, after the model is fit, we are providing a path for model to create files. We are saving the fitted model already for each symbol in our list of symbols. Why do we save that? Because Arima stores the estimated coefficient, state space, differencing logic. And later, if we want to recreate this, it won't cost us cheap in terms of resources. After this, returning fitted model, it allows immediate prediction, testing, debugging if we need. Also, later on, we are wrapping all this into the try except exception, which really is a key to make sure that our pipeline persists and is not affected by any occasional flow that can affect it. This is all. Before next session, I want to go over one more mod. Create RNN model. Self. Put shape, which will be tuple, integers, and this should return time frame, Keras, TensorFlow, sorry, Keras model. So this method is for RNN, and I forgot to tell you about this in Arima, but if you think what we started in previous session, here you can see the Arima guideline, and here you can see the RNN guideline. All these articles are here from May 2024, and feel free to check them. You can find there a separate code for models which were producing prediction in CSV format, not in Streamlit, but that can help, and the deeper explanation can help you going over the timeline and the values and why we are selecting certain parameters. So feel free to explore these pages at Medium. Check, search for my name and last name. I believe I'm the only one there with that first name and last name, so that should help you. Let's continue to our method for RNN, and online will be that create RNN model with optimal architecture. Okay. For this, we are going with declaration model equal sequential, and within the sequential we are providing parameters what sequential with. It goes with LSTM 128 as the unit number, return sequence is input shape is input shape. Then we will go over some more parameters here. Dropout will be 3. We will include batch normalization. We will also include LSTM 64 with sequence equals false. False. And we'll go normalization, drop out 3. Dense 32 actual lucky and dense 1 activation. And next we will go with model compile optimizer to Atom. Learning rate is 0.001, clip norm 1. Loss square and metrics here and metrics equal to mean absolute error, and here are returning the model. Okay, what is different in here? The main difference here comes with comparing to Arima and previous ones, that we are not saving the model yet. You see here we are immediately saving and possible to reuse then with the dump of the data. For previous 3 models that worked. For this one it doesn't. It comes of the nature of RNN model. We will have a specific method to train the model. Now we are just creating it with parameters for the model, which type of the model we are going to use, which algorithm we are going to use, what will be the parameters of it, the dropout rate, etc., etc. So this comes as a part of the model announcement, and at the end we are doing an action of calling the model with optimizer, which is selection is Atom, with a learning rate and clip norm, with announced loss, which will be one of our tracking parameters of mean squared error, and the metric we are going to follow is mean absolute error. So this creates our RNN method, which we are going to train later. Now, what we are going to do next? We are going to create also a LSTM model, which will be similar to RNN. Let's create it, but we're going to work on the code of the create LSTM model. So input shape will be equal the same as before. It will be tuple of integers, and to return again TensorFlow class and after this method going to work on prepare sequence data. The data will be prepared for those for the last two methods because we need for RNN and LSTM to have improved pre-processing of data to normalize the data and to prevent scaling issues. So yes, we are going to have specific method for data preparation for these two models, and after that we are going to create code for training this data. Basically, LSTM is comes with the same more or less code as was RNN, so why don't we just simply copy this, or we will do that on the next session. We talked about this one. Now let's announce the next method that we will be working on. Prepare sequence data. So data will be numpy array, look back integer 3, and we will return the tuple array p and d. So this is what we are going to work on next, and today we created the RNN model and Arima models, so get ready for our next lesson. We will basically reproduce the RNN code for LSTM model and prepare our data stream to flow for later training of LSTM and RNN models. Hope you enjoyed the lesson, and see you at the next one. Bye bye.